Then next up we have a remote speaker, which is Weixin Chen, who's going to present global and personalized graphs for heterogeneous sequential recommendations by learning behavior, transitions, and user intentions. Let's see. Here we go.
Hi everyone, my name is Weixin Chen. I'm a PhD student from the Department of Computer Science at Hong Kong Baptist University. I'm so honored to present our paper, which is global and personalized graphs of heterogeneous sequential recommendation here. This paper was finished when I was a graduate of Shenzhen University under the supervision of Professor Weike and Professor Zhong Ming. So the problem we aim to solve is that predicting the next likely to purchase the item for the users with his or her interaction sequence, which consists of pairs of item ID and behavior type. We call it heterogeneous sequential recommendation, that is HSR in short. So the reasons why we focus on this problem are mainly 2 points. The first one is that most existing works for HSR ignore the correlations between different behaviors. Another reason is that they usually model the behavior information without considering the effects of contextually relevant interactions. To address these 2 issues, we propose a node solution utilizing global and personalized graph for HSR to learn the correlation of different behaviors and user intentions. These 2 types of graphs from our solution could address the mentioned limitations respectively. There are some works relevant to our work, for example, BPR as one of the most representative works on recommended systems, which is based on a pairwise assumption that users prefer interactive items to uninteractive ones. There are also some remarkable works for sequential recommendations. For example, Sasrico first introduced attention technique to weight each item in the interaction sequence. GCE is similar to our work. However, it doesn't consider the effects of different user behaviors. Those works for heterogeneous sequential recommendation are most relevant to our work. MGN Esprit is closely related work to ours that captures the sequential information and distinguishes the impact of different behaviors via GNN. However, most work for HSR split one sequence into multiple sequences according to the behavior types on items, ignoring the correlations between different behaviors. This is the illustration of our module, and we will describe all the layers in detail. So the first one, we will describe the input and embedding layer here. As formulated is for obtaining feature vectors for item ID, behavior type, and precision ID. So we can get item embedding, behavior embedding, and the precision embedding from the input and embedding layer once we input the required data. And then we will describe the global graph layer. So this is an illustration of global graph layer. First of all, with the goal to model the behaviors in a more general and common way, we categorize all behaviors into 2 major types, that is examination E and purchase P, where examination E denotes all related positive non-target behaviors such as clicks, aids to cart, and favorites in e-commerce sites, and purchase P represents the target behavior. Then we construct a global graph of items and behavior transition for all users and to learn information of different behaviors correlations. For each node V, it represents an item I. We first classify the neighbor groups regarding the node V by 6 edge types. For example, E to P plus represents the transition is from examination behavior to purchase behaviors, and is an invert for the node V, and the reason, and then we generate its neighbor groups and obtain the corresponding update vectors for each type. Note that we treat the transition of same behavior and the transition of different behavior differently. Specifically, we do not consider the directions for the same behaviors transitions. That's because for different behaviors transition or age, we should identify the behavior on items linked by it. But for the same behaviors transition, the behaviors are the same for both side items. Then we combine the inward and outward update vectors to obtain update vector for transitions of different behaviors. So we can get 4 update vectors for E to E, E to P, P to E, and P to P, and use a gating network to decide different ways for them to obtain the final update vector. And then we can obtain the global graph representation for the node V. Then we come to the personalized graph layer. For the part of personalized graph layer, we constructed for the users by his or her interaction sequence. Different from global graph layer, we fuse the behavior information into the node in this layer as structured information. In personalized graph is not as significant in the global graph, and we learned the local contact information by considering inward and outward edge for node V. We first collect its neighbor groups and then calculate the update vectors, just like that in global graph layer. Then we could get the personalized graph representation for the node V. So after obtaining the global graph representation and the personalized graph representation, we introduce a fusion layer to combine them. This is the illustration of the fusion layer. It calculates a value gamma U to balance the effects of global and personalized representation for user U. And by fitting the sequence into the graph and fusion layers, we could get a graph representation for each interaction in sequence. And we also applied an attention layer to distinguish the different importance of each interaction and capture deeper relationship. Is an illustration of the attention layer. Note that the attention technique we used is quoted from Rico, so we do not talk too much detailed information about the technique used in attention layer here. So we can take the last output of this layer as the final representation of the interaction sequence. Then we introduce a prediction layer to generate the top K recommendation. As illustrated, we utilize the target behavior vector and the final representation to make prediction for all uninteracted items. After calculated predictive probabilities of all candidate items, we adopt the cross entropy loss function for model training. And we use 4 public data sets on experiments and follow the data sets processing in BART, which is another word for HSR. This is the statistic of the pre-processed data set. For evaluation, we use hit rate at 10 and undistributed at 10 as the evaluation matrix. Note that we generate recommendation from all uninteracted items for each user. For baseline, we choose 2 matrix factorization-based algorithms, and for non-GNN based algorithm, including attention-based algorithm Rico and IB, RNN-based algorithm GRU for Rico, and CNN-based algorithm Kaiser, and 2 GNN-based algorithms as our baselines. These are the details about the parameter settings. And here are the main results. We could have some observations that first, our proposed GPGSR showed a superior performance in the range. We can see that it only performed the second best on Rico 15, which is slightly worse than SRGN, and it may be because of more than 90% interaction sequence in RecO 15 exists a continuously subsequence of click status examination, which takes more than 60% length of its parent sequence. So there are insufficient correlations between different behaviors, as there are more continuous interactions with same types of behavior in RecO 15 than in other data sets. Hence, the results clearly demonstrate the superior performance of our model. Second, we compared our model with RecO. We found our model superiors it on all the first data sets, which means that the input embedding landed by our graph and fusion layers capture more relations of behaviors and is capable to distinguish the user intentions of same behavior with different context information. So we also conduct other experiments in this paper, but not discussed here. So we turn to, yes, here. So in this paper, we address two limitations of existing work for heterogeneous sequential recommendation, that is modeling different behaviors separately and learning the user interest balance behaviors without considering the context information. To address these two issues, we propose a novel solution called the GPG for HSR, which captures the transitions of behaviors via a global graph and learns the user intentions of different feedback with adjacent interactions via a personalized graph. Extensive studies on our public data sets demonstrate that our GPG for HR achieved the state-of-the-art performance compared with several competitive designs. Ablation study also showed the design of our graph layer and fusion layer is reasonable. For the future works, we will take the user's privacy into consideration and design some GNN federal learning-based measures for study problem. Moreover, we are interested in exploiting some tactile information such as the user's reviews and the items attributes to further improve our model. So thank you for listening, and if you have any question.
Thank you, Weixin. Thanks. We've been getting questions online. The highest voted question we have right now for you is about the complexity. So what is the time complexity of the different layers? What's their parameter size? And is this model scalable to very big data sets?
Well, that's not a difficult question, but we do not exactly compute the complexity of our model, but it's like about for movie length data set is about the same time consuming of the such RecO do. So that means our model is not too much actual parameters than such RecO.
Okay. Yeah. All right. The other question is about efficiency. So how much data is required to learn from and is it the same for all of these different behaviors? Are they weighted equally?
Sorry, I couldn't get it.
Oh, I'll repeat. So do you know anything about the data requirements? How much data do you need for it to work well?
Okay, so exactly, we do not need extra data. We just construct the graph from the original data set, like using its behavior sorted by the time order.
Okay, all right. Weixin, thank you very much for answering our questions.
Okay, thank you.
Let's thank the speaker once more.